Again, you're still on icosanoids, no? Part. Okay, so in general, no, if you just eat properly with good food, nice food, and katong mga foods that have very high, that would have high content of omega fatty acids, no, it would really promote to continue the usual biological processes in our body, no? And of course, the result would have like good skin and no interruptions with all the biological processes in our body. Okay, so for lipids, the physical properties of the fatty acids are largely determined by the length and degree of unsaturation rather of the hydrocarbon chain, and the nonpolar hydrocarbon chain accounts for the poor solubility of fatty acids in water. Okay, expect your fatty acids to be not soluble in water, especially when the carbon chain of fatty acids is taas na. If, for example, you have acetic acid like two carbons, no, and then you have C double bond OH, expect it to be soluble in water like suka, no. It's soluble in water even if you have because you have the C double bond OH, the carboxylic acid, which would introduce the hydrogen bond interaction with water. So it becomes soluble. So you have your satiety. That is for acetic acid or the ethanoic acid. No, kanang yung suka. It's majority composed of the carboxylic acid, ethanoic acid. Now, in the case of fatty acid, which usually has the hydrocarbon chain range from 12 to greater than 20, no, the hydrocarbon chain is very large, no, that the nonpolar end becomes large. So the nonpolar end overwhelms the polar end of the fatty acids. And for that reasons, that fatty acids becomes insoluble in water. They have poor solubility. And in fact, it's the reason when you mix oil and water, no, they don't mix together because oil usually comprised of fatty acids, which fatty acid has a large part having the non-polar end. Okay, see the structure earlier. Even if there is a polar end for a fatty acid that would introduce hydrogen bond with water, no, but it is being overwhelmed by the hydrophobic end or the non-polar end of our fatty acid. Again, so even for simple fatty acids, there is a poor solubility with water. And the longer the fatty acid chain, and fewer the double bonds, the lower is the solubility in water. And the carboxylic acid group is polar and ionized at neutral pH. Ionized, when I say ionized, so if you have the C bond OOH, it becomes ionized in water. You would expect that the acid is dissociated, so it becomes C bond OO minus. The carboxylates, it becomes negatively charged, and the proton hydrogen is dissociated in water. So, and because of that, the carboxylic acid group accounts for the slight solubility of short chain fatty acids. Kung short lang ang fatty acid chain nato, like less than 10, no? Somehow na siya solubility in water. But the higher the number of carbons of fatty acids, the greater would be the insolubility in water. Again, the double bond in oleic acid restricts rotation and introduces a rigid bend in the hydrocarbon chain. So because of the double bond, it doesn't rotate around the double bond. So there is a rigid bend in the hydrocarbon chain like this one. Now you don't expect this to rotate unless we have single bond can be rotated. But this double bond, don't expect that to be rotated around single chain length around the double bond. Melting points are strongly influenced by the length or degree of saturation you have here. And for example, at room temperature 25 degrees Celsius, the saturated fatty acids from 12 to 24 have a waxy consistency, whereas unsaturated fatty acids of this length are oily. So expect this, no? Imagine this one, there is a strong interaction between this. what would be the kind of intermolecular force of interaction? You have learned, excuse me, you have learned that in your general chemistry and organic chemistry. Of course, there are different kinds of interaction depending on whether it's polar or non-polar. And this end, the polar end, this head end, no, the residual man OOH, you expect this one to have ionic interaction or the hydrogen bond interaction. Okay, but to this case, this one, or you can also have this type of interaction. In this case, there is no polar atom here, and everything here is non-polar. So the only force of interaction that you would expect are the van der Waals interaction. There's hydrophobic interactions. Okay, and even if it just utilizes the van der Waals force of interaction because it is very long, it's very long, contains at least 12 to 20 fatty acids, and it would promote a high melting point, as I mentioned earlier. And because this is linear, again, there's strong interaction, you expect this kind of saturated fatty acids to be waxy, more like of a solid. No? For example, kung naamoy oil, kanang mga lard, it easily contains kanang saturated fatty acids. But if in case you have your samples to have a higher number of unsaturated fatty acids, kinky, so imagine if this would have a van der Waals interactions, no hydrophobic interactions. But the moment there is a kink, no, the distance between this chain length and this another chain length would be greater, and the van der Waals interactions becomes weaker, no, because they are not situated close to each other because of this kink. So what will happen? It will affect on the melting point. So because there is a weak intermolecular force of interaction due to the van der Waals interactions lessened and van der Waals interactions, what will happen is that the melting point will be lessened. Gamay ang melting point. So kung gamay mo na melting point, there is kink, no? So what happened is ma-allow ang fluidity between this. Kaya naman siya certain distance and the interaction is much lessened. So mas fluid ang atong samples of fatty acids that contains a higher number of unsaturated fatty acids. So they are like fluidy or oily. So if you compare kung the same number of carbon nga saturated siya. So kung inani siya saturate, how do you say, waxy na siya, solid na siya, but if you have the same number of carbon chain length and then na siya double bond, medyo oily pa siya. Okay. So then you choose, no? If na may oil sample at home, which one would you like? Katong matulog bilang nagiingon, no? Mo solidify na siya or katong oily. Okay, so that's why I have mentioned earlier which sample at home, no, that you did observe na matulog, oil samples at home na matulog, or which oil samples at home nga kuan. Maski pag ibutang nimo sa rep, no, kuan gapon siya. Maski pag bugna ang panahon, oil liquid gapon siya. Okay. So again, this difference in melting points is due to different degrees of packing of the fatty acid molecules. There is a different degree of packing here. You can see. This one is highly packed. This one is during a part pack, but about 3, they're not packed. Again, this will affect on its physical properties and also what we observe. Okay. So you just familiarize yourself with this. I have already mentioned this. Note on the trends. You have 12 to 24, for example, and it's even this for saturated fatty acid. There's this structure, there's this systematic name, and there is this common name. And you've noticed here that the increase in the number of carbon atoms for saturated fatty acids, you expect the melting point to be higher. And I expect the melting point to be higher because the greater the number of carbons, the greater would be the van der Waals interaction with each other, and the greater would the intermolecular force of interaction, the higher would be the melting point. Okay, so since you increase in the number of chain length here, what you would expect is that it becomes insoluble in water. But if mubo lang ang number of carbons, there is somehow solubility with water. But of course, as compared sa atong non-polar solvent, for example, benzene, you expect these fatty acids to be highly soluble with organic solvent, non-polar organic solvent. For example, benzene, or for example, if we have another organic solvent, no, like carbon tetrachloride, like or methane, you expect these fatty acids to be soluble with non-polar organic solvents. Again, so here is the non-saturated fatty acids, unsaturated rather. So you have here the delta, which means the double bonds situated in particular carbon. There is the systematic name again, and there is this common name. Usually what you see again on food products are the common names. Okay, so you just have also to be aware, even if you know the systematic name, also know the common name, because you see this one, the systematic name is still very long. No? We don't want that sa atong, if you are a manufacturer, if you are the analyst or the marketing officer, you don't want your consumer to be like, what is this? Okay, what is this name? Cis is nice. It's very overwhelming. So you'd rather show them the common names for your fatty acids. No? And some of them are actually the omega fatty acids. Again, so these fatty acids are, their main source actually are the animal fats and plant oils. But these animal fats and plant oils, you don't usually just straightforward see the fatty acids. No, what we see in animal fats and plant oils are our triglycerides. So what is a triglyceride? So the triglycerides have this structure here. It's triesters of glycerol. So kanang glycerol kani is our glycerol. You have tulo ka carbon and you have your OH here. And esters of glycerol, which means esters gani. Esters, you have your C double bond O. That is our ester. This is the functional group of ester. So esters of glycerol, this is our triglyceride, and this is where you will find your fatty acids. You'll see in the structure. So here is your carbon 1, 15 plus 1, 16. Okay, 16s are all no double bond. So this is saturated. This is the source of your palmitic acid. From the palmitate, from the ester of glyceraldehyde, you have this palmitate. And if you dissociate this one, you can actually obtain your palmitic acid. So this one is oleate, and you can get your oleic acid here. Okay, and you have your stearic. You dissociate this one, you actually get your stearic acid, 18,081 here. Okay, so as the name indicates, the alcohol of triglycerol here, you have your alcohol. If you dissociate, you actually recover your glycerol. So again, our source of fatty acids, like kaning ating gipang mentioned, the simple one, or you have the C double bond OH, or carboxylic acid, no. In reality, you don't usually just see that one as a free fatty acid. No, it's a bounded fatty acids in animal fats. And I say free, in antibody, you already have the C double bond OH in a free structure where you just see siya getting different fatty acids. But we see actually our bounded fatty acids, bounded to the triglyceride structure. So our source are of the triglycerides. Our source of fatty acids are the animal fats and plant oils. So even if you have your plant oils, no, it's not a free fatty acid. It's still a bounded one. And this is our source, like this one. So if, for example, you have a different plant source, you have a different animal source. So this structure here, this mixture of, for example, palmitic, stearic, oleate, no, it will vary. For example, if your sample is coconut oil. So this one would vary, like how much percent would this be? How many of this will have this palmitate? Like, would there be another one, like chloric, for example, laureate? No. So that will be the case. What else? So in contrast to the alcohol part, the acid component of glycerides may be any number of fatty acids. So these fatty acids do, however, have certain things in common. Number one, fatty acids are practically all unbranched carboxylic acids. So what do you mean by unbranched? Gani, no? Branching gani is like if you have this fatty long chains of hydrocarbons, just like what you have learned in organic chemistry, branching is a straight chain of hydrocarbons na carbon here, somewhere here in this long chain. Carbon. So what you notice here that our fatty acids are not branched. Okay? Ang makita lang natin diri is kaning okay siya. This is not branching. This is due to the double bond. No, na siya kink diri. Dili na siya highly organized. Okay? So fatty acids are unbranched. Carboxylic acids, they range in size, about 10 to 20 carbons they contain, an even number of carbons. You've noticed that, I don't know why God chooses the structures to be even, no? But usually in nature, the fatty acids are even in numbers. So apart from the COH group, they have no functional groups except that some do have double bonds. So the only functional group that you usually see is the acetyl bond O, when it is being dissociated in water. Again, the carboxylic acid in water, it's an acid. We've learned in general chemistry that in water, acids are dissociated. For strong acids, our acids are 100% dissociated in water. For example, HCl, now in water, it will dissociate completely to become H plus and Cl minus. And H plus would again be surrounded with water, it becomes H3O plus, not the hydrogen ion. For carboxylic acids, now it's an acid, there is a certain dissociation. It's not 100%, but there is this part that it will dissociate, certain degree that it will dissociate. So for example, 9% dissociated or pila ka percent. No? So what will happen when it becomes dissociated, it becomes, the carboxylic acid becomes COOO minus. This one is dissociated, hindi mo siyang COO minus, and there is that H plus to be in solution. And that's the reason. That's how we define our acids and bases. Remember, no, acids are substances that produce H plus in water or dissociates to H plus in water. That's the Arrhenius definition of our acids and bases, right? So that is the reason you have here carboxylic acids in water to be dissociated. And of course, what do we name? You always have to know that it is derived from this carboxylic acid. So we name as oic acid. Oic, so there's always an acid part. Okay, again, so the functional groups we can see is only the COH. They have no other functional groups that you can find. In most fatty acids that have double bonds, again, mabalik-balik ni, they are the cis isomers predominant. We don't usually see the trans, but it's always the cis that predominates. Even cis, okay, have that. What else? Balik mani. Again, so you have seen in the structure earlier that the triglycerides are complex mixtures. Although some of the molecules contain 3 identical fatty acids, in most cases 2 or 3 different acids are present. You see in the earlier example now that there are different kinds of fatty acids that's being bonded to our triglycerides. But there are also cases when there are identical fatty acids that's being bonded to our triglycerides. Again, that would depend on samples of animal fats and plant oils. What else? Triglycerides are the most common lipid material, although mono and diglycerides are not infrequent. So triglycerides, meaning there's 3 esters that you can see in the glycerol, in the esterified form of glycerol. The hydrophobic character of triglycerides is caused by the long hydrocarbon chains. And to say how we characterize our fatty acids in its free form is also how we characterize our triglycerides. No? We expect our triglyceride to be hydrophobic, to be insoluble in water, because of the esters of the fatty acids there that's being present. So when you have a long hydrocarbon chains, you expect your triglycerides to be having a hydrophobic character. And the ester groups, once you have your acetyl bond O minus, you've learned it again in organic chemistry and in general chemistry. Those are polar atoms. Those are electronegative atoms, the oxygen. You expect that in the bond between carbon and oxygen, you expect your oxygen to be the one that will bear the partial negative charge, and carbon becomes the partial positive charge. You expect that there is a dipole in the bond between acetyl bond O. Acetyl bond O, no? Kato structure niya, particularly that it assumes a trigonal symmetry. Okay, so you expect that the ester groups, so esters or carboxylic acids, no, because you have the acetyl bond O minus or O for esters, you expect that those functional group are polar and those that you have only the carbon hydrogen tail are the non-polar. So the polar groups, the ester groups, and the carboxylic acid groups for your fatty acids are buried in a non-polar environment, which makes the triglycerides also insoluble in water. Again, so how we characterize our free fatty acids is how also we characterize our triglycerides to have the end which is polar and to have the end which is also non-polar. So asa man na tan-aw na to ang structure. Kani diri, this becomes our polar end, kaning a chain becomes our non-polar end. This becomes the polar end, kaning polar end, kaning chain length niya nga hydrocarbon, this becomes the non-polar end. Okay, again, our fatty acids here that you can see are bounded to the triglycerides. They are not in the free form na fatty acids that what we have previously discussed in the previous example. But that is our source of our fatty acids, the triglycerides from animal fats and oils. So for the reaction, just in case you wonder how you would actually obtain your triglycerol, triglyceride, is the reaction between a fatty acid and a glycerol. So imagine here you have the OH and you have the carboxylic group from your fatty acid, how it's being prepared in plants and animals fats. It's always a reaction between the fatty acid and this, and you have the first OH of the glycerol is the reaction with your fatty acids. You have the monoacyl glycerol minus waters in the process of forming for the reaction of carboxylic acid and alcohol. So the O here will attack the carbon here, zero bond O, and turning OH will left. It will take with it the hydrogen here, so minus OH and hydrogen here, you get minus water in the process. Okay, you have another here, can you see and another ROH, so it will react with the second carbon here. So again, see OH will react to the carbon here, and the OH will be liberated along with the hydrogen here. So you get this one again, C-1OR. And then until you react to the last OH from one to the ethyl glycerol, another carboxylic acid, then you produce your triacyl glycerol. This is now your triglyceride. And your R would depend now whether it will be on the same fatty acid or would it be this different. So it could be a mixture, it could be the same. And so this is just know that this is your acyl group. You have your acetyl bond O, and this is from your triglycerol part here. So formally defined, a triacyl glycerol is a lipid formed by esterification of three fatty acids to a glycerol molecule. The glycerol and your fatty acid, that is your triacyl glycerol. But you notice here that you need 1, 2, 3 moles of fatty acids in order for you to prepare your triacyl glycerol. Of course, because you have to form an ester here. Of course, you need 3 moles of your fatty acids, or your fatty acids could be the same, or your fatty acids could be different. And that is how your triacyl glycerol or triglyceride is being prepared. When the name triacyl, within the name triacyl glycerol is the term acyl, and acyl group is the portion of the carboxylic acid that remains after the OH is removed. Again, it's an acyl group. You have your carbonyl acetyl bond O. This is the ester, acetyl bond O, but without this O, it's just call this one to be the acyl group. So when you deesterify this one, you have your acyl group. Thus, as the name implies, triacyl glycerol molecules contain 3 fatty acid residues attached to glycerol residues. And other name that's frequently used for triacyl glycerol is triglyceride. Now, so in case nag-confuse pa mo, triglyceride and triacyl glycerol is just the same. Okay, so here again is the structure of your simple triglyceride here. Here you have the glycerol tripalmitate. You see tripalmitate, all of the esters here in your triglycerol or triglycerol is the same, no? So you have your acyl group, the same, yeah. But again, this esters here could be different. This acyl groups here could be different. But in this case, no, it's all palmitic acid. But when you dissociate, actually, we get our palmitic acid, fatty acids here. So you have your 14, 15, 16, okay? So what happens is that this can be dissociated and we actually get our free form of fatty acids from your triglyceride. You get your glycerol and then you get your, once this one is hydrolyzed or acid water, when it reacts with water, rather, you actually get your free form of fatty acids like kidney. And then you get your OH here. This one will become free once it reacts with water. And you have your free fatty acids, this one. So 3 moles of the same palmitic acid here that you can see. Okay, but again, depending on the sample, this acyl group could be different, no? But it could also be the same. So, but in this case, all of these fatty acids here in the bulk form are the same. So you get the same 3 moles of your fatty acids here. Okay, so again, how to prepare this triacylglycerol is the hydrolysis of water, dehydration process rather. In the dehydration process, in the reaction of glycerol and fatty acids, that you liberate water. Of course, in your reverse reaction, your water will be incorporated here to get your free form of your fatty acid. So if this water and your triglyceride will react, now liberate, you can get your free form of your fatty acids here and then your glycerol. But you synthesize your triglycerol, you have here, and water will be liberated. Okay, it's very simple. In this case, you have a mixed triglyceride. Here you have your myristic acid, you have your palmitic acid, you have myristic, you have 11, 12, 13, 14, and all single bonds. Palmitic also, you have all single bonds. Now you have 13, 14, 15, 16. And oleic, it's there's a double bond. So here is a mixture of fatty acids that's being prepared. And again, if you react this with water, you'll get your free fatty acid form. But to prepare this one, you need the glycerol and you have the free fatty acid. That's how it is in animal fats and plant oils. So, balik. So here again is your fatty acid triglyceride. No? If we do hydrolysis in the presence of a base, now we can actually liberate this one. When we react this one with water, and in the presence of the catalyst hydroxide, now we can actually liberate this one to get your glycerol and to get your free fatty acid form. So you get your C double bond OO with this chain length here. Okay, C double bond O with this chain length here to form this one. So this is actually the process of how we do the saponification. We just a hydrolysis reaction. We say hydrolysis, we add water to the reaction. Kani reverse siya ni. Kung kani mo react sa water in the presence of a catalyst hydroxide, no? When you get a hydrolysis reaction, we actually get this free. So kung i-reverse natin yung reaction, paingon diri and sa right, paingon sa left, i-reverse natin, that is actually a hydrolysis reaction and we'll be able to get our free fatty acids. Okay? But here what is being shown is baliktad. We're trying to form the triacylglycerol. Pero baliktaron na itong reaction, this water that will react with glyceride, makakuha na ito ang kani, free fatty acid. Again, depending na kung sa imong free fatty acid. And in fact, kung kani siya, our triglyceride will react with water in the presence of a base, the hydroxide. It is being facilitated, the reaction will be facilitated when there is a base, the hydroxide present in solution. You actually get this one. And that becomes actually a saponification process here. And let's see if we can prepare. Yes, We can do soap preparation in the lab. But I was actually thinking if we do the preparation of mayonnaise in the lab. So yes, we can prepare a soap, no, from our oils. So I think that would be a good experiment. Even at home, you can do that. Okay. So what is the time ba? Okay pa. What else? So here, again, so here, once you have your glycerol and you have your free fatty acid, you can form your triglyceride, that is esterification. The reverse is the saponification process, wherein you add water to this and you will be able to recover your glycerol plus your free fatty acids. Kulangan man ilang kan, the free fatty acids here. What else? So here is ano ba man eh? There should be a single bond anihan na kuan na ni siya na single bond na. So please do not mind the double bond. It's only a single bond. So this is your glycerol here. In Sage-2, there should be a double bond here. Dili na siya triple bond. No, please correct your slides if you're able to print this one. To update this. Dili na siya nakuan na ni siya pag print siguro, no? Sa paper. But this is only CH2, single bond, CH, single bond, CH2, like this one, no? And this is just pseudo bond, o dili na siya triple, na manobra na si carbon ng bond. Please note, no? Basin maglibog mo na unsa na ang structure. So when carbon number 2 is chiral, carbon number 2 is chiral in ester chains at positions 1 and 3 are different. Yeah. Easily not. So for example, here you have the different one, this becomes chiral. You learned that in your organic chemistry, you know, when carbon atom is bonded to 4 different group of atom, 4 different groups, then your carbon becomes chiral, and there's a certain stereochemistry for that. One structure will be the mirror image of the other. Okay, so you have your mixed triglycerol, but when you have the chain length here in carbon 1, carbon 3 are different, and this carbon here becomes chiral, but usually not like this one. The same, so this one is not chiral. So what else can we learn? So again, fatty acids commonly found in animals as triacyl glycerols, which are stored mainly in adipose cells, the adipocytes. No, it's formed by esterifying glycerol 3 times. Katong reaction bitaw natong nakita no with glycerol and fatty acids. No, first reaction will be the first OH. Second is the 1,2 glycerol formation. The second is the triglyceride formation, triglycerol formation. Okay, so what is can also be learned with triacyl glycerols or the triglycerides? It's a major energy source for many organisms. So take note for that. And most reduced form of carbon in nature. Efficient packing, it's highly hydrophobic and aggregated into non-hydrated lipid droplets, and compared to polysaccharides, which are highly hydrated. Now you notice that polysaccharides, there's a lot of OH in the structure, no? Because of its monomers, monosaccharide. It's always OH. And you expect that there's always, with the OH, you expect that there will always be hydrogen bond formation with water, and therefore, for most polysaccharides, they are hydrated. But here with lipids, with fatty acids, your triacyl glycerides, so cutting apart, they're highly packed. This becomes the polar end here. And when they are together with another mole of your triacyl glycerides, what will happen is kaning si polar group, polar end will be situated to be close to the polar end of another molecule of this triglyceride. That what happens is that for the packing, kaning polar end will be kanang situated to each other, close to each other, while the hydrophobic end will be situated also to each other, for a maximum interaction. And that's is being mentioned here, highly hydrophobic and aggregate into non-hydrated liquid lipid droplets rather. So this one is the non-hydrated form. You notice in the structure because of course you don't see any polar groups here, unlike when you see in your carbohydrates or polysaccharides. And as main source of energy, proteins and carbohydrates can actually recover 4 kilocalories per grams. For ethanol, it can have your 7 kilocalories per gram. For triacyl glycerols, the fats, your animal fats and animal oils can actually get 9 kilocalories per gram. So there's more energy per gram if you eat a lot of triglycerides, animal oils, animal fats, and plant oils. So other advantage for users of triacyl glycerols is used for insulation and energy without nitrogen, and you can have the metabolic water formation once you have the oxidation, you have your carbon dioxide. Oxidation would yield to carbon dioxide and water already. So here, what is the difference between fats and oils? Animal fats and oils. So fats contains a great proportion of saturated fatty acids than unsaturated fatty acids. FA fatty acids. May shortcut man gini nila. Fatty acids. Basta you know, no? Pagkatapula na balanggit. What's the difference? You notice that for fats, na it's more of a solid or a semi-solid at room temperature. In oils, it's more of a liquid at room temperature. That's how we define by the layman's term, and it's true. Usually, you have your beef tallow, your pork lard, animal fats usually are solid at room temperature. Pag iinit mo, of course, hindi mo makita, ka-liquid man siya, but when you store it at room temperature, even sa ref, you see this, example, the beef tallow, pork lard, they would solidify. Okay, but for soybean oil, canola oil, even at low temperature, at room temperature liquids, yeah. And again, why would that be? So from this physical state alone, you will imagine or you will remember that the main source or the composition rather of this for this liquid oils would contain a greater proportion of unsaturated fatty acids. We have discussed that earlier. And for those that are mostly solid would contain a greater proportion for your saturated fatty acids, katong walay double bond. For the oily, for the liquidy oils, like soybean oil, canola oil, peanut oil, expect that there is a greater proportion again of unsaturated fatty acids. So your source, animal source, usually called your animal fat, and vegetable source, you have your vegetable oil. Although kanang sa market, the vegetable oil usually comes from, although mostly are from vegetables, right? But vegetable oil usually comes from kuan. Anyone, gikan sa lubi, coconut oil. Okay, and for other sources, they call it corn oil, like canola oil, sunflower oil, jojoba oil, kanang pang beauty products na mga oil. Okay, but usually they term, although we know that vegetable source is essentially called vegetable oil, but here in Philippines, vegetable oil is referred sa gikan sa katulubi. Okay,